Welcome to Tech Talks with Applied Catalysts, where our mission is to highlight new trends in industrial catalysis and manufacturing through informal discussions with partners and colleagues in the field. I'm your host, Ben Egelske. I'm the Senior Chemical Engineer at Applied Catalysts, supporting catalyst development and catalyst manufacturing. And today I'm excited to introduce two guests. The first is our senior chemist at Applied Catalysts, Dr. Greg Tate. Dr. Greg Tate has a long history of catalytic experience going back to his bachelor's at the University of Tennessee, through his PhD at the University of South Carolina, and his most recent postdoc at University of California, Berkeley. Dr. Tate is an expert in chemical kinetics and is well versed on a long history of industrial topics. The second guest and our external guest is Dr. Ihor Tarnavchyk. Sorry, Ihor, I should have asked your name. Tarnavchyk. Can you say your last name? I apologize.
Tarnavchyk, that's correct.
Tarnavchyk. Principal scientist at Renuvix LLC in Fargo, North Dakota, supporting development of composites and coatings from renewable feedstocks. He's got a BS, MS, and PhD from Lviv University in Ukraine, and he continues to stay active in the field as a Fulbright peer reviewer and journal reviewer for polymer chemistry. So I'm really excited for this show today. This is the first time Ihor and Greg have met, and I think there's going to be some good synergy here. So just to kind of tee it up, I know last week or 2 weeks ago when I called you, Ihor, I said, hey, do you want to be on the Applied Catalyst podcast? You said something to the effect of, I would love to, but I'm not a catalysis person. I'm a application scientist. And that really spawned this really cool discussion about what that means, what oleochemicals mean and so on and so forth. So if you can just tee up, what are oleochemicals, and then just high level, what do you do? And we'll just kind of spin off from there.
So basically the oleochemicals are all the materials and chemicals you can make out of fats and oils. If you think about fatty esters, starting from biodiesel, or things like soap and surfactants that we regularly use, these are oleochemicals. And there are a lot of others. Like I'm focused on polymeric products that you can make out of oils, out of plant oils. And everybody knows alkyd resins, right? So you make alkyd resin by converting soybean oil, into its derivatives and then polymerizing it into an alkyd. And there are lots of variations, not only alkyds, just simple example.
So Ihor, I got a follow-up.
Yeah.
Go ahead.
I got a follow-up question for you. So for the listeners, you said we start with soybean oil, but let's go back a little bit further. We have a plant, we have a seed, we're extracting oil out of that seed, and then we're making a final product. Could you give us a brief description of how you go from plant in the field to your material?
Yeah, I started from soybean because that's a major raw material for alkyd, just as an example. And there are variations of fats, right? So you see fats of animal origin. You can convert them, and that's how people started making soap, from fats. Now, these days, I think plant-based oils are major source of different oleochemicals, because easy to grow, relatively, short period. You make it in 1 year, produce the crop, collect it, extract the oil, and then you can clean it up and convert it into a number of things. Of course, we look at seed oils as a source of nutrients. We use it in food a lot, but on the other hand, there are a lot of industrial uses, and we use it in cosmetics, we use it as lubricants, we use many other applications. So we can just break down each of these applications like cosmetics, for example. Oils are converted into glycerides. If you look at any composition of any cream or hair product, it will have some sort of glyceride in it, monoglyceride, diglyceride, or oil-based surfactants. And now, if you think about the sources, there are oils that come from palm, oils that come from seeds like soybeans, corn. Many industrial agricultural products have oils, and we can extract these oils, clean them, convert them into different derivatives.
So when you're
So
looking at these applications or these molecules, do you typically start with end application in mind, or do you start at the beginning and say, hey, we think this structure will be good for potentially these fields?
Well, fats and oils have different compositions. If you look at chemical structure of oil, it's a triglyceride. It has glycerol and fatty acids in its composition. So typically, a glycerol has 3 fatty acids. Like it's trifunctional alcohol. So each hydroxyl group is occupied with a fatty acid, and then the fatty acids are also different. So you can see there are short chain, medium chain, and long chain fatty acids. So starting from 8 carbons to like 14 carbons, these are considered medium chain fatty acids. Everything above is long chain fatty acids. Also, these fatty acids might have double bonds, which also contribute to the properties of oils, and they might be saturated, no double bonds, mono unsaturated, and polyunsaturated. Depending on the composition, if it has mono unsaturated double bond, or if it has polyunsaturated fatty acid, then the variation of properties will be dramatic. So it might be liquid or solid. That's why we need to understand the composition of the material we're looking at, and then we like what chemical modification needs to be done to get certain properties. For surfactants, I know that short medium chain fatty acids are primary primary raw materials, like lauric acid, which is a C12 fatty acid, and saturated fatty acid is used to make most of the surfactants currently available on the market that are used in cosmetics and hair products. For other applications, like lubricants, we can use mono and polyunsaturated fatty acids. They are liquid. We can convert them into different types of esters, diesters. We can use oils directly as lubricants. And also soaps are another type of lubricants. They provide boundary lubrication. Sometimes people use soaps as lubricants in industry as well.
So you mentioned earlier degree of unsaturation, monounsaturated, saturated, polyunsaturated. What are some of the properties that are most significantly impacted by the number of double bonds in a triglyceride set of chains?
Well, first of all, if you think about the same length of fatty acid, for example, C18, which is very common, then the level of unsaturation will affect its melting point, the oil melting point. It might go from like liquid oil, like corn oil or soybean oil, to viscous, more viscous and even solid product. Let's say if you compare like butter, it's kind of solid, semi-solid. or if you fully hydrogenate or fully saturate these double bonds, then you'll get hard material. So that's major property. Another important thing is oxidative stability. That is very important for industrial use. For example, one of the reasons people started looking into saturating these double bonds is because oils tend to oxidize. They capture oxygen from the air and produce different byproducts, produce aldehydes and low molecular weight acids that affect all its properties and start degrading pretty much. So one way to overcome this is to saturate these double bonds with hydrogen and make them fully saturated products.
And that's good that you brought that up, because at least in our field, catalysis, the saturation of oils and fats is one of the longest industrially practiced catalytic processes. It's been
Yes.
done since the early 1900s, certainly.
I think for the general public, I don't know if people quite understand how big the oleochemical industry is and just how many products come from natural plants. I mean, you mentioned cosmetics, lubricants, and so on and so forth. Do you know approximately how big that industry is globally?
It's hard to tell. Honestly, I haven't done such like market research, but I know it's growing based on an article I recently read that they expect the industrial use of soybean again, because it's a primary source of oleochemicals in the US. The primary use of the market is expected to double in 10 years, and that's just for industrial use of soybeans.
It's pretty amazing. I know the
yes.
soybean is very versatile on what you can do with it. Can we discuss a little bit some of the transformations that you do to go from soy type A to soy type B?
Well, soybean oil is interesting because it's more or less consistent in composition. It has mono and polyunsaturated fatty acids in it. But if you look at the chain lengths, so it's primarily C18 fatty acid. It only has 10% of C16 fatty acid in it. And I mean, if you can hydrogenate, for example, these double bonds and make it into like fully saturated fatty acids, the composition is very consistent. So it's almost everything is C18 stearic esters, right? That's one reason. Another reason is it's inexpensive. It's relatively easy to produce. Farmers are interested in growing soybeans, and the current price, I think, of soybean oil compared to others is like the lowest. I think palm oil, it might be a competitor, but again, soybean, if you look at potential uses, has way more industrial applications compared to palm, because it has double bonds that you can still utilize in some other applications in thermoset chemistry. Well, what you can do with these oils and how you can use them for industrial application. First thing, it depends on what application we're looking at. Sometimes you can use them directly, running minimum number of transformations. You can epoxidize it, for example, and use it as epoxidized product. So what you do is epoxidation. You oxidize these double bonds and make epoxy group, put epoxy function on them, and that also affects oxidative stability. That improves oxidative stability. So now you eliminate all these side reactions, and oxidized oil is still liquid, and I know people use it as processing aid and plasticizer in plastics. That's one of the major applications. There are a number of other conversions that you can do with epoxidized oil. You can make it into polyol and use in synthesis of polyurethanes that are partially bio-based. Other transformations would, there are a number of transformations that you can do on the carboxylic site. So then you have to pull and separate glycerol from these fatty acids. That's what we typically do. We replace glycerol with different sugars and convert them into totally new oleochemicals, way more functional oleochemicals. But that's a little bit more complex, and number of transformation reactions include primarily hydrolysis and esterification, sometimes aminolysis, and we can talk a little bit about that. I think transesterification is very common, or reesterification is very common reaction. If you're familiar with biodiesel process, that's how biodiesel is typically made. Oil is reacted with methanol, and then it produces methyl ester and glycerol as a separate byproduct. One of the reasons the biodiesel process is so popular because it allows you to separate these fatty esters, then fatty acids. If you think about the oil composition, you have monounsaturated fatty acids, you have polyunsaturated fatty acids. Now you have different chain length, and for industrial use you want to have more uniform composition. You have to be in specs. The only way to overcome it is either hydrogenated oil to remove all the double bonds, or as another option, you have to separate them. And you can separate them by distilling them in fractional distillation. So you can separate monounsaturated. They vary in boiling points, which is, and you can use the tool of distillation. But that requires a lot of effort, and it's not really inexpensive tool to use. So then if you look at hydrolysis, of course, if you want to make hard soap, you can either run saponification or hydrolyze the oil into glycerol and fatty acid, and then neutralize the fatty acid with potassium hydroxide or sodium hydroxide, depending on which soap you want to make. Another interesting thing is, I wanted to bring that topic too. So biodiesel is an interesting product because it's easy to make. Just the nature of this process, the esterification or re-esterification process is an equilibrium process. So you put two products and then you have like everything in equilibrium. But because glycerol is not really miscible with oil and the final end biodiesel, it tends to separate and drive this reaction to high yield. So it's more than 99% yield. Very easy, you can make it at room temperature. Just put a catalyst and the alcohol in there. But it doesn't work for any transesterification. It's just for making biodiesel using methanol. And that's another reason why people use it a lot.
It's actually pretty fascinating. You get if you can exploit the chemistry to do a self-separation to drive your equilibrium, that's a huge tool. I see why that process took off. because separations and esterification is a big challenge in the
It
industry.
is.
It's a space we're actually developing some art in and engaging people out there to say, how do you do your separation, right? And then people get into azeotropic distillation and having to handle entrainer molecules and simplest case, you can just do a simple flash separation in a overhead condenser. But a lot of the times that process is pretty complex.
Especially with the catalysts. To separate a small amount of that catalyst, which you use. Now I know they tend to use, and you're more specialized in that, in heterogeneous catalysis. So when you can put a catalyst on solid substrate and just reuse it, you don't have to separate it. Is that right?
It's the ideal case.